structural analysis to chapter 8 deflections using energy methods. Let's solve another example in beams and just assume we have a two simple support beam handling distributed load by a two triangular part with the intensity of W. We want to know what the delta maximum at the center of the beam is. At the support A, we have a pin, and at the support B, we have a roller. Let's see how we can approach this problem. So if we just cut the beam by a length of x, just assume if we are in the half of the bay, which is L over Q, we have the intensity of W at the top here. You can easily see the intensity at the L equal to L over 2 half of the length. So let's cut the beam through by a unknown length of x and then see what is the intensity at the length of x if you travel from A to B, and it just turns to be 2x over L times W. That's the intensity, 2x over L times W. That's the intensity at the length of x. And if we want to convert the distributed load to a concentrated load at the centroid, it just tends to be a half of the intensity times distance triangular half of that, and it just turns to have a force like W over L times x squared, and at the distance of 1/3 from the base. Now if we just develop the moment equation, we can jot down the moment equation, and then by integrating the moment equation you will get the theta, and by integration of theta equation you will get the delta. Placing in our integration by the boundary condition, and can easily get the delta maximum. This is our first solution, which is integration method, which is the most conventional method to calculate the theta and delta for any kind of beam just by integrating from load or moment function. So as soon as you have that, and then by having the boundary condition, it just gives us C2 is equal to 0, C1 is a this numeric value, and then as soon as you replace to the main equation for theta, it just gives you for y, it just gives you delta maximum of a negative, it's just downward movement WL to the force over 120 modulus of elasticity time moment of inertia, and theta at A, which is equal to theta at B, it just gives you again negative 5 WL cubed over 192 EI, which is again coming from replacement in theta equation. This is the most common method from integration. You can also solve this problem with the moment area method. So let's jump to solution 2, which is moment area method. By moment area method, it just says T A with respect to tangential line, which is drawn from A with respect to a horizontal line from C. It just M over EI area under moment times X bar, which X bar is considered from the first point. So that's all. Area T A over C tangential moment A from C is the area under moment, which is here. We can easily calculate that, and times the X bar. I will provide the link for that video if you want to see the whole process for integration method and also moment area method. But today's video, we are interested to solve it from a structural point of view, which is the virtual mode. So in virtual mode, which is our third method, the first one was integration method, the second was moment area method, and this is the virtual work method. So as soon as you have the moment equation in virtual work method, the real moment is just replaced like capital M in equation. And if you remember, that was if you apply a one, if you want to calculate delta at center in virtual work, we just apply 1 unit of load at there, and the equation is just 1 times delta C vertically is equal to small m capital M over EI dx from 0 to L. Then we just easily calculate delta, vertical delta, the vertical deflection at point C, which is the center. And for virtual work, for a small moment, we just place the 1 unit of load and then calculate a small m of x at the distance of x. If you do so, and definitely that 1 unit of load is evenly distributed between A and B, then summation of moment about x goes 0 counterclockwise, considering as a positive moment, it just gives us mx minus a half, a half of x equal to 0, and it just gives us a mx, which is the effect of virtual moment, as we didn't have anything over there, and we just get the all component to replace in the virtual work equation. And this is virtual work. In virtual work, we have a 1 times delta CV if you just apply a 1 unit load here, and then times, due to symmetry of structure, you can just go by 0 over L over 2 and multiply by 2m times capital M over EI, then integrate it from 0 to half of the length. Then as soon as you have that one, you can easily replace the moment. This is the real moment effect. This is the effect of virtual moment, which we already calculated. Small m x is equal to 1 over 2 times x. And if you just place the attributed appropriate moment, like capital goes by real one and small m goes by virtual one. And if you just replace for the integration, this is the small m, this is capital M, and it should be have e over e over e. I don't forget e over time. That's a constant show up in the denominator. So as soon as you do that, it just gives you this integration, and by simplifying that integration, it just gives you numeric value for calculation. This is 1 over 240, and 2 of that, it just gives you 1 over 120 WL to the force over EI, which was exactly what we were looking at. So it just gives us a W delta maximum happens at the center, and numeric value for that is delta maximum is equal to WL to the force over 120 pi. If you remember, we just had it with integration method. We had it with a moment area method, and now we had it from structural. These two are from mechanics of solids approaches, and this one is just come from virtual work, which is a structural approach in more detail. In next video, we will talk about the calculation of theta at A with all these three approaches. Thank you.